In this video, we'll be learning how to differentiate a function from first principles. Now, the idea here is to remember that the definition of a derivative is f dash of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x over h. And we can actually differentiate just about any function using this rule. Let's see how this is done. Let's say we're given some function, and we'll start simple. Let's say we're given a function f of x equals to x squared. Now, to differentiate this from first principles, we're going to use that formula and state that f dash of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x over h. But now, in our function, which in this case is f of x equals to x squared, if I were to replace x by x plus h, it would become x plus h in parentheses squared. So let's go ahead and write that. We would have the limit as h tends towards 0 of, I replace f of x plus h by x plus h in parentheses squared, x plus h squared, minus f of x, and f of x is still just x squared, over h. Now, expanding that first set of parentheses inside there, this will lead us to the limit as h tends towards 0 of x squared plus 2hx plus h squared minus x squared. Again, all of that's still over h. And we can simplify this a bit. We can see that we have an x squared here and another one here which is being subtracted, so they cancel out. So this is going to be equal to the limit as h tends towards 0 of 2hx plus h squared divided by h. And again, we can simplify further. I can see that there's a common factor now on all of these terms. There's an h here, an h squared here, so I can get rid of one of them, and an h here. All of the terms are being multiplied by h, so we can get rid of that common factor. And so the next line would be the limit as h tends towards 0 of 2x plus h. But now when we take the limit as h tends towards 0, this means that we're looking at the value of this expression here when h becomes infinitely close to 0, so close that we can't distinguish h from 0. So what kind of value is this expression going to get closer and closer and closer to the closer h gets to 0? Well, hopefully you can see that if 2x plus h, if we let h become infinitely close to 0, then 2x plus h will just become infinitely close to 2x, because the h will become nearly negligible. And so we can write f dash of x, and now we no longer have to write the limit, is simply equal to 2x. And there we have it. We have just differentiated f of x equals to x squared using first principles. Let's look at another example. Let's say we had to differentiate f of x equals to 2x squared plus 1. Again, using first principles. Well, again, we would start by writing f dash of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x over h. And since f in this case is 2x squared plus 1, then what we have to do to figure out what f of x plus h is replace every x we see in our function f of x by x plus h. So in this case, we're going to have to replace this x here by x plus h. So that would lead us to f of x plus h equals to 2 times, in parentheses, x plus h squared plus 1. In other words, what I'm saying here is we have f dash of x is equal to the limit, as h tends towards 0, of 2 times, I replace x by x plus h, so x plus h squared plus 1. And I have to subtract from that f of x. And now I have to start parentheses because f of x has more than one term, so I want to make sure I subtract them all. And we do that using these parentheses. And we divide everything by h. Our next job really is to clear this up a little bit because we can't work with this right now. So we're going to start by expanding these brackets. Limit as h tends towards 0 of 2 times x plus h squared is x squared plus 2hx plus h squared plus 1 minus, I can open up these parentheses, 2x squared minus 1. Remember, when you open up parentheses which are being subtracted, all the signs change. Again, all of that's over h. Now I can distribute this 2 across these parentheses here onto each of these 3 terms, and that will lead us to f dash of x is equal to the limit, as h tends towards 0, of 2x squared plus 4hx plus 2h squared plus 1 minus 2x squared minus 1. And again, all of this is being divided by h. Now looking at this, we can see that a few terms are going to cancel out here. I have a positive 2x squared, which is then going to subtract 2x squared, so they will cancel out. And I have 1, which is going to subtract this one, so they cancel out. And so I'm now left with f dash of x is equal to the limit, as h tends towards 0, of 4hx plus 2h squared over h. And just as in the previous example, I can see that all the terms here have a common factor, which is h. So I can go ahead and cancel all these h's, and I can cancel that square h there. So we'll now be left with f dash of x is equal to the limit, as h tends towards 0, of 4x plus 2h. But now, to take the limit, you need to ask yourself, looking at the expression 4x plus 2h, what type of value or what expression is that going to get very, 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 very close to if h gets very, very, very close to 0? In other words, if we consider the expression 4x plus 2h and we're told that h is infinitely close to 0, well then this term here, 2h, is going to get infinitely close to 0 as well. So in essence, we're just going to be left with that 4x. And that's what we're doing here. We're taking the limit. So we're saying that f dash of x is going to be equal to 4x. And there you go. We've just differentiated this function from first principles. Remember, our initial function was f of x is equal to 2x squared plus 1. And we've just found that its derivative is f dash of x equals to 4x. And there you have it. That's how you differentiate from first principles.